All right. Good afternoon, everybody. It is exactly the top of the hour right now, and we are going to give about 3 more minutes for the room to fill. We usually begin our program at 3 minutes after the hour. All right. Welcome, everyone. Thank you all for being here. Welcome to our July 2025 installment of Intercalc Office Hours. If you're a regular, you know the drill. We have a few housekeeping items to get going on. If you're joining us for the first time, we'll go ahead and go through these just so that we have everything all set up for you guys today. So before we get going, I want to start with a quick sound check. If you direct your attention to the bottom menu of the Zoom window in either your browser or your desktop app, you'll see the chat tool or the reaction emojis, whichever you prefer to use. If you're able to hear me right now, just go ahead and throw us an okay, a thumbs up, something in the chat, or the reaction emojis work just fine as well. That is perfect. Thank you all so much. Now that we have confirmed that, before we get to the rest of our housekeeping items, we also want to go ahead and do a quick sound check and visual check for our primary speaker today. Chelsea is going to go ahead and share her screen. And then once again, if you can hear Chelsea's voice here in just a moment, and you can see her screen as well, go ahead and give us a thumbs up or an okay.
Hello, everybody.
Awesome. Thank you guys for confirming that. Now that we have our tech checks out of the way, we are going to go ahead and disable the chat, and then we'll move on to some introductions and get going with today's program. So my name is Seth Roseworm. I'm a senior structural engineer and software developer here at Intercalc. And our presenter for our monthly Intercalc Office Hours program today is Chelsea Darnell Zhang. So a lot of you know Chelsea already. She's a product engineer here at Intercalc, and she tends to split her time between providing technical training for Intercalc customers, working with the Intercalc engineering team on the specifications and technical behavior of our software, offering customer support to our users, and also helping maintain a presence for Intercalc at national and regional structural engineering events throughout the industry. So before joining Intercalc, Chelsea was an engineer at a structural engineering firm in the Bay Area, San Francisco. And during that time, she worked on a variety of different projects, everything from high end residential homes to elementary schools, public parks, seismic retrofits. She's also an active member of the SEOC Pathways program, which aims to advance structural engineering in California by improving recruitment and retention of underrepresented groups in the profession. For anybody who's new this month, the Office Hours program is meant to provide simple, direct communication lines between us and our users, and there's several different avenues by which we do that, mainly showcasing new features and updates, letting you guys know every month what's new in Intercalc, what's happening in the program. We also do design spotlights and show optimized design workflows. We answer questions that have been submitted ahead of time in writing. We also do live Q&A with the audience at the end of every session. If there's ever a question that's too involved or it's going to require deep dive troubleshooting, this will be a better fit for the support team. They can investigate your concerns, kind of look under the hood in the program and get you better answers for your questions. As a minor point of order, you will notice that everybody's microphones are muted just to make sure we don't get any echo or feedback during today's program. And of course, as I mentioned, we always do have an open Q&A with the audience at the end of the session today. To submit a question for today's Q&A, just use the Q&A dialog in the lower dashboard of your window. If you experience audio problems at any point during the session, you can always either refresh your browser or jump out and rejoin the session. And if you ever want to rewatch today's program or any of our previous Office Hours programs, or you want to share it with someone on your team who wasn't able to see it, the recording will be posted to the Office Hours playlist on Intercalc's YouTube channel, which you can also access from our website. And with that, I'm going to go ahead and hand it over to Chelsea to get us going on our program for today.
Awesome. Thanks, Seth, for the introduction. And hello again, everyone. Welcome to another session of our monthly Office Hours program. As Seth said, I'm Chelsea, and I'm excited to be presenting to you all today. So I want to start our session with a brief overview of today's agenda. We're going to be covering an announcement about PDHs for Office Hours, Intercalc's latest build, what's new in Intercalc. We'll be going through an example using the cantilevered retaining wall module in Intercalc. We'll discuss how you can register for Office Hours so that you're notified. And then at the end, we'll have a live Q&A. So as Seth said, please feel free to drop your questions in the Q&A form throughout the presentation. So starting in May, we began offering 0.5 PDH credits to Office Hours attendees to reflect the guaranteed technical portion of each presentation. So please note that the name on your certificate is going to match the name that you used to join the Zoom session. So be sure to enter it exactly as you'd like it to appear on your certificate. And then within about a week, you're going to receive an email with a link to download that certificate. Now, as many of you know, Intercalc releases monthly updates, and we want to make sure that our users are taking advantage of the newest features and program capabilities. So we do often receive support questions where users mention maybe a missing feature or a discrepancy between their hand calculation and the program output. And in many cases, these issues are simply due to the user running an outdated build. So the team actually just released a new build this morning, and we encourage you all to take a moment to update your build and make sure that you're running the most current version. So if you could all just take a minute to open your software, you're going to see your current build at the top of the program. If you're on an outdated build, you can easily download the latest version of Intercalc by selecting the Update button in the upper ribbon. So clicking on the Update button is going to open the window shown on the left, where you can check for updates and access the For Our Users page to download the latest build. On the For Our Users page, you can navigate to the Software Download section to install the latest build. And then once the file has downloaded, you can simply launch it, and then you'll be up and running with the latest and greatest version of Intercalc. In this window, you can also subscribe to new build update emails. These emails include release notes that highlight newly added features, bug fixes, and other important updates. If you'd like the program to automatically check for updates at program startup, you can also select this button below, this checkbox. A quick note for users on builds 2023-0830 to 2024-0228. The automatic update notification feature is not functioning properly. So if you are affected by that, the user will need to update manually one time, either from inside EnterCalc or through the website. Now, if you've not been on the latest build, or maybe you haven't had time to poke around in EnterCalc recently, we wanted to take a minute to highlight some of the newer features and functions that we hope that you can take advantage of. First, let's discuss the updates to the building codes. As of March, IBC 2024 is now supported as a governing code option. To update your project to use IBC 2024, you can go to General, Building Code Information from the Project Manager, select the IBC 2024 option, and then you can save and close. And a reminder, since EnterCalc has decoupled the ASC 7 edition from the governing building code to provide greater flexibility, don't forget to also set your preferred ASC 7 edition separately within that same window. This same menu can be accessed by clicking on the building code and load combinations button at the top of EnterCalc. Either way, this method will change the code for only the current project that you are working in. If you would like EnterCalc to default to IBC 2024 for all of your future projects, you can start by going to Settings in the top left corner of your screen. From the drop-down menu, you can select Default Governing Code and ASC 7 Edition Building Code Information. And then in that window, you can choose IBC 2024. Again, since EnterCalc has decoupled the ASC 7 edition from the governing building code, you'll also want to set your preferred default ASC 7 edition, such as maybe ASC 722 or 716, depending on your jurisdiction's requirements. The next update I'd like to highlight is the addition of new ASC 722 modules. Previously, the ASC seismic, wind, and other loads and force capabilities came preloaded into every EnterCalc project. But with the introduction of ASC 722, we've decided to make a change. So these modules are now treated like all other modules in the program, meaning you can choose which ones to add to your project, giving you some more control and flexibility. As shown here, the last three tabs are the newest additions, and these can include calculation modules for ASC 722 seismic, wind, live load reduction, and snow loads. To add an ASC 722 loads and force module, you can start by navigating to the building code information window and then setting your ASC 7 edition to ASC 722. Then when you return to the project manager, you can click Add and select the desired module from the tabs we viewed on the previous slide. If you wanted to view previous ASC 7 loads and force modules, you'll need to go to your building code information window and then set that ASC 7 edition to either ASC 710 or 716. And then when you go back into your project manager, you're going to see the seismic, wind, and other loads and force folders. So you can open and edit these calculations as needed. Next up is my favorite feature to share, and that's native load linking within EnterCalc. Load linking gives users the ability to automatically link reactions from one calculation to another, and the ability to change something in one member and then have the effects of that change trickle down to all the supporting members. Load linking is currently available for wood beams, wood columns, steel beams, and steel columns, and our development team is actively working on load linking for other modules as well. If you'd like to learn more about load linking, be sure to check out our load linking playlist on YouTube. It features a series of short videos that walk through key features, tips, and tricks to help you get the most out of this tool. And we've also added a new video recently that's from our May office hours, where Mac walks through a complete example of how to use load linking to transfer reactions from beams to columns. And this example covers both wood and steel materials. The next update is the ability to export tabular detailed results from EnterCalc to a CSV file. This is going to be useful to many engineers who want to do some post-processing of the results outside of EnterCalc. And all you need to do is go to the results that you're interested in. You can right-click on the table, and then you'll see this new menu appear. And you can click on Save to CSV to download that file to your computer. And this option to export CSV results is now available in all modules that have tabular inputs like this. We also have an exciting update to the general footing module. By popular demand, you now have the option to specify top reinforcement in the footing. So this is perfect for situations where tension occurs at the top rather than the more typical bottom tension. You can define the rebar size and quantity separately for each direction to suit your design needs. And then this table on the far right shows sample results, including a helpful note from EnterCalc indicating whether tension is at the top or bottom. So this makes it easier for you to adjust and optimize your footing sizes. The last item that we want to highlight is EnterCalc for Revit. EnterCalc for Revit is a Revit plugin that allows you to leverage EnterCalc Cell to design structural members fully within Revit without having to export information to another calculation software. So by linking EnterCalc with Revit, EFR helps speed up your single component and element design by leveraging key information like your beam spans and load linking relationships directly from your Revit model. It also provides change tracking and management capabilities, minimizing transcription errors, and ensuring that your calculations and model remain accurate and up to date. Currently, EFR supports the design of steel beams, steel composite beams, wood beams, steel columns, and foundations. And now the moment we've all been waiting for. We're going to move on to our main event. The focus of our session today is the design of retaining walls using the cantilevered retaining wall module in EnterCalc. So we're going to be covering the module's capabilities and limitations by walking through an example together. I want to start with a quick overview of the capabilities and features of the cantilevered retaining wall module. So the best use of this module is for the analysis and design of cantilevered retaining walls. The module allows the user to choose between EFR and Coulomb methods for lateral earth pressure. The module supports a variety of applied loads, including toe and heel surcharges, axial loads on stems, adjacent footing loads, lateral loads on stems, as well as seismic and wind forces. And the module is going to check soil bearing pressure, overturning stability, sliding stability, and masonry stems when ASD is selected for service level demands, as well as concrete footings, concrete stems, and masonry stems when SD is selected for strength level demands. It's also important to note that the module does have some limitations. So this module is not intended for the design of pool walls or aqueduct walls. The module is specifically designed for walls that retain earth. So while you can account for a water table that adds load to the wall, it's not going to be suitable for designing walls that retain water only. The module assumes that the wall will rotate away from the retained soil, which is why you see the heel reinforcement placed at the top of the footing. So in cases where high axial loads might cause the wall to rotate into the retained soil, potentially reversing that heel bending, it might be more appropriate to use EnterCalc's wall footing module to evaluate that kind of condition. Currently, the module does not support the Rankine lateral earth pressure method. We understand that some users would like to see this option reinstated, and that is something that we're considering. And then the module does not automatically evaluate multiple load combinations at this time. So this differs a little bit from the behavior of some of the other EnterCalc modules. And we'll dive a little bit deeper into this limitation when we review the load factors tab. For today's example, we're going to pretend that we have been asked to design a concrete stem retaining wall. Our wall is going to be retaining 10 foot of soil with a backfill slope of 5:1. We're going to have a 5-foot tall fence above our wall with an applied wind load of 30 PSF. And then we have a 100 PSF heel surcharge. And our geotech has provided us the soil values shown here. Our design is going to be based on IBC 2024. And I'll be mentioning some differences between ACI 31819 and 31814 as they come up. So let's jump into our EnterCalc program, and we can start a new retaining wall calculation by clicking Add, navigating to the Earth Retention tab, and then selecting the cantilevered retaining wall module. We're going to start with our inputs in the General tab, and then we'll work our way through the inputs moving left to right to set up our calculation. So here on the General tab, we can give our calculation a unique name, and then we can jump into filling out our other inputs. First, we're going to define 3 key heights. So this is the retained height, the wall height above retained soil, and the height of soil over the toe. The retained height and the wall height above the retained soil are going to help establish the overall geometry of the wall. Later in the STEM tab, we can specify additional details such as wall thickness, wall height, and indicate the elevations where different sections might apply. Next, we can define a level backslope, or in our case, a 5:1 backslope. One thing to note here is that the sloping backfill angle is always going to be projected upward and to the right of the wall. At this time, the module does not support downward sloping backfill. When a soil slope is specified, stem calculations are going to be based on the retained height at the face of the stem, so they're not going to include the additional weight from the soil wedge behind the wall. If you're using EFP, so the equivalent fluid pressure method, the program is not going to adjust the EFP value that you input to account for the slope, but it will calculate the retained height at the back of the heel, which might be greater to the slope. So for overturning, sliding, and soil pressure calculations, the retained height is going to be projected vertically at the back of the heel. The program will also add a surcharge for the weight of the triangular prism of soil over the heel. On the other hand, if you choose to use the Coulomb method, the slope is going to be factored into the final calculated pressures using the appropriate equations. So next we can define a water table height. If we're designing for a water table condition, this is where we're going to enter the maximum height from the bottom of the footing to the water table level. The program is going to use this input to compute the added pressures for saturated soil on the heel side of the footing. Enercalc is going to assume that the submerged weight of the soil is 62% of its dry unit weight. And because this module is not intended to be used for pool walls or aqueduct walls, it's not recommended to specify a water table height that is greater than the retained height. So that's something to keep in mind. Next, we're going to define our soil values, which typically come from the project's geotechnical engineer. For lateral earth pressure, we have two options. We can use the equivalent fluid pressure method or the Coulomb method. When the equivalent fluid pressure method is selected, the engineer will enter active and passive soil pressures in PSF per foot of depth. And again, these values are usually provided by a geotechnical engineer. When the Coulomb method is selected, the engineer will enter the soil friction angle in degrees. This value is usually provided by a geotech from soil tests, but it can also be found in reference books or building codes. And then once this value is entered, Enercalc will use this value along with the soil density in the standard Coulomb equations to calculate the Ka and Kp multipliers. And then these multipliers are going to be applied to the soil density to determine the active and passive soil pressure values. For our example today, we're going to be using the EFP method. As you can see, I've entered the values for both active and passive soil pressure. I've also specified a soil density on both the heel and toe sides, as well as a soil spring reaction modulus. And the soil spring reaction modulus is going to be used to determine the tilt of the wall, which we'll discuss more when we look at our outputs. In this section, the engineer can specify whether the vertical component of active soil pressure should be used for soil pressure and footing design, overturning resistance, sliding resistance, and global stability checks. When these checkboxes are selected, the vertical component of the lateral pressure is going to be applied at a vertical plane at the back of the footing. When EFP is used, the program will back solve the Rankine equation to find the equivalent internal friction angle, phi, and then when the Coulomb method is used, the phi angle is going to be specified by the user. So Enercalc takes this phi angle and uses it to determine the soil wall friction angle. So the way it does that is if there's no heel projection beyond the stem, the failure plane is assumed to be at the soil wall interface. So the program is going to use phi over 2 for the soil wall friction angle. But if there is a heel projection, like we have in our example today, the failure plane is going to shift back to the end of the heel, creating a soil on soil interface. So the program is going to use phi as the friction angle. And then that friction angle is then used to determine the vertical component of the active lateral soil pressure. Moving on to our loads tab, this is where we can enter the applied live, dead, wind, and seismic loads to be considered in the wall design. We can specify surcharges, axial loads, adjacent footing loads, and lateral loads. For surcharge loads, we can apply live load surcharges to either the toe, heel, or both sides of the wall. We also have the option to specify whether the surcharges should be considered in sliding, overturning resistance, and soil bearing checks with these checkboxes. For strength checks, surcharges are going to use the live load factor that the user defines in the load factors tab. And for service checks, a factor of 1.0 is going to be applied. If a toe surcharge is defined, it's going to be treated as an added soil weight. So for example, a surcharge of 220 PSF with a soil density of 110 PCF is going to be equivalent to 2 feet of additional soil. So this surcharge is going to influence our sliding resistance and our passive pressure at the toe. When a heel surcharge is defined, it is considered to be uniform load applied over the top surface of the soil above the heel. And this can be entered regardless of whether the ground is level or sloped, but it is always going to be treated as a vertical force. And then to convert this to a lateral load on the wall, EnerCalc is going to divide the surcharge by the soil density and then multiply it by the active pressure coefficient. For our example, we have a 100 PSF heel surcharge applied, and I have selected to consider the heel surcharge for sliding, overturning, and soil bearing pressure checks. Next up, we can specify uniformly distributed axial, dead, and live loads that are going to be applied to the top of the stem. These loads are used to calculate stem design values and factored soil reaction pressures used for footing design. One thing to note here is that only the dead load is going to be used to resist overturning and sliding of the retaining wall. This load type allows you to specify eccentricity measured from the center line of the top stem section. Positive eccentricities are going to shift the load towards the toe, and then negative eccentricities are going to shift the load backwards towards the heel. Users should be cautious with high loads and eccentricities that could cause reversal of bending in the heel. Like I mentioned earlier, the module assumes that the wall rotates away from the retained soil, and conditions causing wall rotation into the retained soil might be better evaluated using EnerCalc's wall footing module. When applying axial loads, keep in mind that they're treated as uniform over the 12-inch design strip, and EnerCalc is not going to reduce them along the wall height. So if you're modeling a point load, such as a beam or girder reaction at the top of the wall, the engineer might want to consider reducing the input to reflect how the load spreads downward along the wall. So let's walk through a quick example of what I mean by that. Let's say that I have a 15 kip point load applied to a 2-foot wide bearing area at the top of my wall. In this case, I might consider reducing the axial load input to account for how the load spreads as it moves down the wall. So this is typically at a 2-to-1 slope. This spreading effect can reduce the compressive stress at the base of the stem. So since the stem design is based on forces at the base, a user might choose to enter an axial force of 1.25 KLF, which is that 15 kip point load spread over an effective width of 12 feet, and then perform a separate hand calculation to check the local effect of the 15 kip point load on the top of the wall. Now, if I do choose to reduce the axial input, I'll want to consider how many stem sections I'm evaluating. The compressive stress is going to vary along the wall height. So if I'm analyzing multiple stem heights, it might be necessary to create a copy of my retaining wall model and test different axial inputs for each height. Now, this example is simply intended to illustrate how an engineer might apply loads and evaluate the wall based on specific conditions. Whether or not you choose to reduce axial loads is entirely up to the engineer's judgment. Moving on, users can also specify adjacent footing loads. Users have the option of placing a footing, line, or square adjacent and parallel to the back face of the wall and have its effect on the wall included in both the vertical and horizontal forces on the wall and footing. Boussinesq analysis is used to calculate the vertical and lateral pressures acting on the stem and footing, and adjacent footing loads will be factored by the live load factor for strength design. When the line load footing type is selected, the user should enter the continuous load per foot parallel to the wall, along with the footing width and any other dimensional information required for EnerCalc to perform the Boussinesq analysis. Now, if the adjacent footing is another retaining wall at a higher elevation, the Boussinesq analysis may be used to account for the vertical load applied to the soil from that adjacent wall's footing. However, the design should also probably account for lateral sliding forces from the adjacent wall, and this lateral load could be entered as an added lateral load, but doing this is at the engineer's discretion as it is beyond the scope of the program. Users should also note that the program does not currently perform any type of global stability analysis of tiered retaining walls. When selecting the square footing type, the user should enter the total load divided by the footing dimension that runs parallel to the wall. For example, if I have a 2,000-pound load on a 4-foot square footing, I would enter 2,000 pounds divided by 4 foot, so 500 pounds per foot in the magnitude box. The user should also enter the footing width and any other dimensional information required for EnterCalc to perform the Booz-Nesk analysis. For our example today, we don't have any adjacent footing loads, so we're going to move on to our lateral loads input. For the lateral loads input, we can apply dead, live, earth, wind, or seismic lateral loads to the stem. For seismic and wind loads, you have the option to specify if load entered is strength or service level. You can specify where the load occurs along the stem to model a uniform load over a certain height. This input can also be used to simulate a point load, like a live load applied to the top of a guardrail. And like axial loads, these lateral loads are treated as uniform over the 12-inch design strip, and they're not reduced along the wall height. So like we discussed in the axial load section, a user might want to consider reducing the lateral load input to account for how the load spreads as it moves down the wall. But again, this is ultimately up to the engineer's judgment. EnterCalc also provides a quick and easy way to apply wind loads on the stem above the retained height using the wind on stem above soil input. You can simply enter the wind load magnitude and then choose whether it's a strength or service level load. For our example, we're going to apply a 30 psf wind load to the stem above the soil, which we will define as our fence in our stem tab. For seismic loading, we can choose to apply a seismic force from lateral earth pressure and or from the wall self-weight here in the seismic tab. For seismic lateral earth pressures, we can use the Mononobe-Okabe Seed-Whitman procedure or a simplified procedure per a geotechnical report. When the Mononobe-Okabe Seed-Whitman procedure is selected, the user will input a KH factor, which EnterCalc will use to calculate KAE and KA using the proper equations. When one of the simplified procedures is used, the user will input a multiplier or a total load per their geotechnical engineer's recommendations. You also have the option to consider the seismic effect due to the self-weight of the stem. When this checkbox is selected, the user will specify a value of FP over WP, which will then be used to calculate a uniform seismic force in PSF. If the wall has multiple stem sections, each will be calculated separately and accumulated for the base shear and moment. So keep in mind that wind and seismic loads don't necessarily have to be applied at the same time. For our example, I've already compared wind and seismic loading, and I found that wind governs, so we're not going to be including any seismic load in this particular calculation. Moving on to the stem tab, this is where we define the stem sections for our design. The content of this tab is going to vary depending on which material type you select. Stem sections can be concrete, masonry, or fence. And fence is only allowed at the very top of the wall, higher than the retained height, and it is considered to be weightless. When a masonry stem is chosen, the user can specify if the design method should be allowable stress design or strength design. For both masonry and concrete wall types, the user can choose to position the rebar at either the center or edge of the wall. If center is chosen, the rebar distance is going to be half the actual wall thickness. If edge is chosen, the rebar will be located at the heel side of the stem. And the user also has the option to enter an explicit D value for the particular stem segment that they're working on. Users are able to add a maximum of 5 stem segments to match their design intent or to get some more detailed results. So this can be useful when the stem is made of different materials, like in our example where the lower portion is concrete and the upper portion is a fence. Stem sections can also help identify where wall thickness or reinforcement can be reduced for a more efficient design. In our example, we're going to use 3 stem sections. The first is going to cover the bottom 3 feet, where the stem reinforcement will match the toe reinforcement, allowing our toe bars to extend up into the stem. Next, I'll define a stem section starting at 3 feet from the bottom. In this section, I'm going to keep the same stem wall thickness, but I'm going to reduce my reinforcement by dropping every other bar so that I can have a more efficient wall design. And this is commonly referred to as the 50% cutoff. So this example shows how stem sections can be used to adjust the design along the wall height for greater efficiency. EnterCalc provides moment and shear values at the base of each stem section you define. And then one important thing to note is that EnterCalc is going to assume that the reinforcement is fully developed at the stem section. So users will want to check their lap splice and development links to ensure that they're detailing the reinforcement appropriately in their design drawings. Next, I'll define a third stem section starting 11 feet from the bottom. This is going to represent our fence. This section will not have any self-weight. So if I did want to include a dead load from the fence, I'll need to add it as an axial load back in our loads tab. And moment and shear outputs are still going to be provided at the base of this section for review. So we often get questions about stem sections. I wanted to provide this graphic for a little bit more clarity. So this shows which values come from the general tab and then which values come from the stem tab. So something to note here is if I wanted to increase my fence height from, let's say, maybe 5 feet up to 6 feet, I would first want to go back to edit my wall above retained height input in my general tab, and then I could adjust my stem design height here in the stem tab as needed. For the stem tab inputs, users can specify the material type, like we said, so concrete, masonry, or fence, along with the wall thickness, a wall weight multiplier. This can be useful if you want to account for some additional loads, like maybe if you have a stone veneer. Users can also specify the rebar size, spacing, and placement within the wall. And then users can also define relevant material properties and then set their minimum stem reinforcement ratios here. This tab also includes 2 quick access buttons that allow users to jump to the rebar lap and embedment length details and the concrete rebar area details. These sections provide some more in-depth information on the required lap and embedment lengths, as well as the minimum and maximum reinforcement ratios. For today's example, we're going to be designing, or we are designing to ACI 31819. But if we were to toggle between ACI 31814 and 31819, we might notice a few key differences. So first, selecting ACI 31819 reveals some additional drop-down menus for hooked embedment modifiers. And these are going to be tied to the updated hooked bar development length equations of ACI 31819 Chapter 25. Next, there are going to be some differences in the checkboxes below. So for both ACI 31814 and 31819, the option to reduce lap splice by stem stress ratio is going to be grayed out. And this is because ACI 31814 and later do not permit the reduction of lap slice by stress ratio. This checkbox does remain visible but disabled, just to help clarify that this reduction is no longer allowed under these codes. Additionally, you'll see that the checkbox for reduced hooked embedment by AS required over AS provided, so this second checkbox here, is grayed out when ACI 31819 is selected, but it remains active for ACI 31814. And this is because ACI 31819 prohibits reducing the development length for hooked, headed, and mechanically anchored deformed reinforcement. One thing that I want to point out here is that we are aware that this checkbox does remain active when the building code is set to IBC 2024, and our development team is working to address that. Lastly, we'll observe a reduction in shear capacity, and this is due to the code updates in ACI 31819, Chapter 22, which I'm sure you're all familiar with. Moving on to our footing tab, here users can specify the footing material properties, rebar cover, and minimum reinforcement ratios. Users can enter their toe width, heel width, and footing thickness in this section. There's also a convenient quick access button that lets users instantly center the stem on the footing if they need to. The other quick access button is one of my favorite features of this module. It's the automatic width design tool. It allows Enercalc to quickly iterate and determine an appropriate footing width based on your input values. So clicking this button prompts the program to iterate through footing widths until both soil pressure and footing strength meet the design criteria. It is important to note that this function does not evaluate overturning or sliding stability. So users will need to check those safety factors separately once the automatic width design is complete. But this is just a really helpful way to quickly establish a reasonable starting point for footing width based on some of your inputs. Users also have the option to neglect the upward soil pressure. This typically results in a greater heel moment. So if this box is checked, the MU for upward loads is going to be 0, and it will lead to a more conservative design. The user can then specify toe and heel reinforcement. Both sections offer a list of acceptable rebar sizes and spacing options. This section also includes a reminder of the rebar size and spacing at the base of the stem. So if you wanted to match the toe reinforcement to the base of the stem reinforcement, you could simply just check this box. Clicking on the footing and key rebar details button is going to open up a pop-up window for some more in-depth information on the minimum and maximum reinforcement ratios. When a key is specified, this pop-up window will also include some key rebar data as well. And then below the toe and heel reinforcement inputs, there's going to be a reference list for acceptable horizontal reinforcement sizes and spacing. So this makes it easy for you to review these options for your detailing. The next tab allows you to specify whether a slab is present to resist sliding forces, whether a key will be provided, select the sliding resistance method, and input details about the sliding resisting forces to be considered. If a key is provided, you can enter its dimensions and specify whether the program should apply active pressure behind the key. Once the dimensions are set, the key rebar details will also become visible. For today's example, we're not going to include a key, so we're going to move on to the sliding resistance section. Here you can choose whether sliding resistance is calculated using friction and passive pressure or cohesion and passive pressure. And then you can enter the depth of passive pressure to neglect, along with the friction factor or cohesion value, and the percentage of passive and friction resistance to be used. These inputs and limitations are typically going to be provided by your geotech. Users also have the option to select a pier foundation. Checking this box is going to replace the key design and sliding tab with the pier design subtab, enabling the use of drilled cast in place concrete piers. In the interest of time, we're not going to cover this feature today, but if users have interest in learning more about it, we can maybe explore it in a future office hours session. So now let's talk about load factors. The retaining wall modules are a bit unique compared to most other modules because they don't allow users to directly control load combinations. And this stems from their long history, originally developed as part of RetainPro before and being integrated into EnerCalc. Since this module is different than most, I just want to take some time to walk through exactly how EnerCalc processes the load factors that you enter into this tab. First, we're going to start with discussing strength design checks. For retaining wall modules, the user inputs load factors into this tab, and EnerCalc will use these load factors to create one factored load combination for strength design checks. So that's going to include your concrete stem design, concrete footing design, and masonry design when SD is selected. So what does that actually mean? If these are my inputs here on the left, EnerCalc will apply this load combination on the right for my concrete stem sections, footing design, and masonry design when SD is selected. So let's talk a little bit about the strength design combo. Since wind and seismic loads typically don't need to be applied concurrently, users might want to run separate calculations to evaluate wind and seismic conditions. When wind and seismic loads are applied, you'll see some caution notes appear throughout the program, highlighting the need to separate calcs when both of these things are defined. So if you'd like to evaluate multiple strength design load combinations, such as maybe one with wind and another one with seismic, the recommended workflow is to first finalize all your inputs, then make a copy of your retaining wall calculation and run several versions, each with different load combinations input into this load factors tab. So this allows you to compare results and then determine the governing case. Now let's discuss service level checks, which include soil bearing pressure, sliding, overturning, and masonry stem design when ASD is selected. For these service level checks, EnerCalc runs one load combination where all the applied loads are at the service level. So the strength level seismic loads are going to be converted down to service level loads with a factor of 0.7. Wind is going to be converted down with a factor of 0.6, and all of your other load factors are going to be 1.0. So once again, if you need to consider both wind and seismic, or if you want to vary other loads like maybe your live loads, it's best to create a copy of your retaining wall calculation, and then from there you can adjust your load inputs and or your load factors to run separate checks to identify your governing condition. I do want to mention that we're aware of this limitation, and improving how load combinations are handled within the retaining wall modules is on our radar. Jumping back to our example, I've already made copies of my calculation and I know that wind governs. So these are the load factors I've applied here in this tab. And then these are the combinations that EnerCalc is going to run. Now that we have all of our inputs finalized, we can review our outputs. So here we see our results summary tab, giving us a quick overview of our sliding factors of safety, bearing pressure, footing flexure, and footing shear results. We can click through the subsequent tabs to view more detailed results, including the vertical forces resisting sliding and the lateral loads contributing to it. Below, we also see a summary of all the sliding forces and the factor of safety. One thing to note here is that the additional vertical force from the weight of the sloped soil over the heel. So as we discussed when we were selecting the soil slope, the program automatically adds a surcharge to account for that weight of the triangular prism of soil above the heel. We can also see a breakdown of our overturning forces, so both our overturning and resisting moments, as well as a summary of our forces below. Here we can see that the axial live load on the stem is not used for overturning resistance. However, the axial dead load on the stem would be considered if an axial dead load were applied. We can see a similar breakdown of our resisting and overturning moments used for soil bearing pressure calculations, as well as a summary of our forces below and the resulting eccentricity. The Global Stability tab displays the results of a global stability analysis, which evaluates a potential scooping failure through the soil. The program calculates driving and resisting forces along a failure arc, as shown over here on this image to the right. These results are for informational purposes. They're not going to affect your pass-fail status of the retaining wall design. And users should consult their geotechnical engineers to determine whether global stability is a critical consideration for their specific project. And users should also note that EnerCalc does not perform global stability analysis for a tiered retaining wall system. The Tilt tab displays the horizontal displacement at the top of the wall caused by rotation due to compression of the soil under the toe. To determine this wall tilt, EnerCalc divides the soil bearing stress by the soil modulus to quantify the displacement at the footing. And then, assuming the wall and footing are rigid, the program determines the horizontal displacement at the top of the wall based on the amount of rotation experienced down at the footing. Again, similar to the global stability, these results are for informational purposes only, and this is not going to affect the pass-fail status of the retaining wall design. The final outputs tab is the stem tab. This is where we can see moment and shear results for the stem sections that we defined in our stem input tab. This is where you're going to find the moment and shear demand results at the base of the fence. So these values can be used to design the fence to wall connection through supplemental calculations. The stem design values tab also includes sub-tabs to review the rebar and embedment length table and the concrete rebar area details table. The final two tabs on the output side of the screen are the construction and wall loading tabs, and these can be reviewed to confirm that you're satisfied with your final design. So the last feature that I wanted to highlight is the equations button. This button is available across all EnerCalc earth retention modules, and it provides access to some of the reference equations used in the calculations. So users can enter their own inputs directly into these screens to run some quick sample calcs. So this can be helpful if you want to backcheck some program outputs or compare some results to some hand calculations. Alrighty, so before we dive into today's Q&A, I do want to encourage everyone to register for our office hours program to ensure that you're receiving notifications directly into your inbox. If you're interested, you can register by going to enercalc.com/office hours. Or you can go to our website and click on the For Our Users tab, select Get Help Support, and then choose office hours from the menu. This is going to take you to the registration page where you can input your contact info and sign up for the emailing list. And then at the bottom, we regularly update the info regarding the next session so that you're always in the loop. At the same enercalc.com/office hours webpage, we also post all of the unedited recordings of the previous office hours session, and you can find them by just scrolling down the page. So now it's time to open it up for some live Q&A.
All right. Let's dive into some questions. So, question from Mike. I often use this module to design stem wall with footing foundations for buildings. Are there any special considerations for this type of design? So, foundations are interesting because there's a lot of judgment involved in figuring out which tool is the best to model your specific condition. Foundations with stem walls could be modeled using the process that Chelsea went through today if it is an actual cantilever condition with a significant retained height. If you're tied to a slab, then it could be more of a candidate for the restrained top retaining wall design, which is a separate module that we have. And then if you have very minimal retained height, but you do have loads being transferred from the wall, then it might be a candidate for looking at the intercalc wall footing module. So it depends a lot on what kind of assumptions you want to make engineering wise and what your specific geometry and the physical mechanics of your detailing um, to decide which tool is best for that. Question from James. For the export results feature, can you pull information such as moment, shear, and deflection in one single file, or do we need to pull it individually? So there's a couple different answers to this question depending on what you had in mind. There is not a single bulk export capability that lets you take all results from a given intercalc calculation and dump them all in one place. The export capability that you access through the right click context menu in all of our results tables now is individual table by table results access. So if you're looking at shear results or you're looking at flexural results, you're looking at reactions, you're only going to access that specific data when you right click. When you do that right click context menu, then you have the capability to either export in a save as workflow or do a simple copy and paste. So if you have a destination spreadsheet where you want to put all of your data in one place, you can just right click and do a simple copy paste instead of like an export save as that would create individual documents. Hopefully that answers your question. Feel free to ask follow up if you have more. Next question. Chelsea, we usually touch on this one. Do we have access to the presentation afterwards?
Yeah, so the recording will be up on our website. I think I saw a question about slides in there. We don't post the slides on their own, but we do post the recording, and then after the session, we will follow up with some documented Q&A. So any of these like question answers that we've had throughout the session, you'll have documentation on that.
All right, perfect. Question from Steve. Where did you get the 2-to-1 spread on the axial load coming down the wall? So just to be clear on that, and Chelsea, feel free to chime in. I
Mhm.
don't think Chelsea was describing something as far as internal operations inside Intercalc itself. She was talking about a typical engineering judgment approach to load dispersion down through a concrete element if you wanted to do your own reduction of that load as you go down to different segment heights in the wall. Is that correct, Chelsea?
Yeah, so that 2-to-1 is not something that Enercalc considers. It is not something that it does. There is no reduction along the wall height that Enercalc does, which is why if you feel that your load is going to be applied over some kind of effective width, then it's kind of up to your engineering judgment to reduce that load in your input. The 2-to-1 specifically came from I have the Basics of Retaining Wall Design textbook written by Hugh Brooks. It kind of goes into both the approach to retaining wall design and kind of some general rule of thumb, like helpful, you know, ideas for making your wall design efficient, and then kind of some like general practice recommendation. As a software provider, we're never going to tell you how to do your design. The 2-to-1 seems to be kind of a rule of thumb that's generally accepted, but it's not a total, rule end all be all. So if you're looking for a reference, the Basics of Retaining Wall Design is a great reference. I've found it very helpful. Um, but other than that, I don't have a specific source for that.
All right, perfect. All right, next question. I've noticed the allowable shear stress of the stem increases as the stem thickness decreases while keeping other variables constant. This seems counterintuitive. Can you comment on this, or do you think it may have to do with running an older build? Current build is 240304. So, um, glad you asked because we definitely want to get you up to the latest build. As long as your company's subscription is current, you always can go get the latest, greatest update, like Chelsea showed us at the beginning. Um, and I don't recall if Chelsea mentioned this, but we tend to push updates. Our development team does anywhere from at least once a month to sometimes twice a month. So with a March 2024 build, you could be possibly as much as 27 or 30 updates back in terms of feature improvements, bug fixes, stability fixes, new features, building code cycle updates, all kinds of stuff. So we definitely encourage you to come up to the latest build. If you do your update and you're still seeing something you don't expect, absolutely feel free to reach out to the support team and we'll dive into that for you. Okay, and Chelsea did address the question about slides. We don't post slides, but we do post the full videos of all these sessions. All right. Luke had a question about opening projects, and Luke, we're happy to dive into that, but that sounds like it might be a better question for the support team since it's more of a troubleshooting oriented question. So feel free to send that over to the support team, and we'll be happy to dive into that for you. All right, going down the list here. We have a couple questions that came in multiple different. All right, question from Jason. Did you say the common equations dialog was available on other modules? I'm not seeing it elsewhere. Is that just in this module?
It should be available on all the earth retention modules. So you'll see that in the cantilevered retaining wall, the restrained, the gravity walls, basically all the modules that came from Retain Pro. You should be seeing that dialog. And it's the same across all of them. So, some of the equations aren't relevant to the specific module you're in. It's just those are kind of quick access equations for any of the earth retention calculations.
All right, perfect. Question from Chris about attendance for the PDHs. Yes, that's tracked automatically. So if you were here and you were in the session, then we'll take care of sending that out to you. All right. Could you touch on secondary reinforcement mat and the stems of the retaining wall? Talked a little bit about stem reinforcement. Do you want to
Yeah,
go
I
back
can
to
go
that
ahead and
slide where
pull
you were
up.
looking at those inputs?
Mm-hmm. Yeah, so the reinforcement is assumed to be the vertical reinforcement is in a single layer. So you can add that to either the heel side or center in the wall footing. I think for secondary reinforcement, are we talking about doing a mat on either side of the stem?
Yeah, Patrick, feel free to ask a follow up if you have additional
Yeah,
detail on your question there.
currently there's only one vertical mat. So, and that kind of touches a little bit on, the assumed behavior of this module. So this module assumes that your wall rotates away from the soil. So if you need a mat on either side because you're looking at maybe like a reversal of forces, so like seismic and wind in both directions, that kind of condition is maybe better used for the wall footing module in EnterCalc, since this module is only going to look at, forces mainly acting in the direction pushing the retaining wall away from the retained soil.
All right, next question. Can I use this model as seawall design? Chelsea, you touched on that a little bit with regard to tanks and containment of liquid water. Go ahead if you have thoughts on that.
Yeah, so the intent of this module is to be used for walls that are retaining soil. If you have a water table that is above your retained wall or your retained soil height, or if you have only water, if you're only retaining water, then this module is not the best use for that. You might see some helpful information and you might see kind of some unusual results. So we do have a feature request for kind of flood walls and walls that are retaining water. If that's something that you do a lot and you're interested in seeing, you can always reach out to support@intercalc.com and express that need. We do log and track our feature requests, and it helps us prioritize our development projects. So if we see a lot of similar requests start to come in, it's telling us that that's something our users need, and that can kind of move up on our prioritization list. So if you would like to see that, please email us.
All right. Next question. How do we resolve the error for minimum reinforcement in the stem wall? So I assume that's
Um,
referring to a temperature and shrinkage or flexural minimum.
Yeah, so the minimum vertical is noted here, and the minimum temperature and shrinkage is noted here. Minimum temperature and shrinkage, which is the horizontal reinforcement, you can manually override this value if you feel like it's not applicable. If you're getting an error that you need some different minimum vertical reinforcement, then you can change your rebar size and your spacing. You can also go to, let's see here, where do I show? So if you're getting some kind of minimum reinforcement errors, I think that the concrete rebar area details tab over on the output side probably would be of some use to you. This is where you can see what the required area is versus the provided area. So this might be able to provide you with some additional information on what's actually missing. If you have a question about a specific project file and I haven't fully addressed that question, you can always send that file to support, and we can take a look at that specific file for you if you still have some confusion.
All right. And there's a somewhat related question from Mohammed. Could you explain where or how we can see temperature and shrinkage rebars in the footing in the construction tab? Um, so just to be clear, the temperature and shrinkage or the minimum reinforcement that Chelsea is referring to is just a limit against which all your inputted rebar is going to be tested. So we're not explicitly providing temperature and shrinkage bars, I don't think. Go ahead, Chelsea.
Yeah, we kind of show them graphically. I mean, you can see some horizontal reinforcement in here, but we don't explicitly, you know, model them. It's most of the design is based on, your heel and toe and then your vertical stem rebar. And the temperature and shrinkage requirements are provided as informational for you so that it can help you with your detailing.
All right. Um, let's see. Question from Jay about calculation report showing a certain IBC versus what was selected in the UI. Jay, feel free to reach out to the support team about that. That's in reference to the separation of IBC from the individual material design standards. But if you're seeing something you don't expect in your printed report or in the interface, go ahead and grab us a screenshot of that and send that to the support team, and we'll be happy to take a look at that for you. All right. Question from Frank. Does the module check shear friction of the footing dowels? So it sounds like he's referring to where the stem actually meets the top of the footing, um,
Mhm.
whether that's actually doing a shear friction check where the dowels anchor both of those elements together.
Yes, that's a really good question. I I'm not 100% positive on if that check is completed and what that check looks like. I can definitely look into that and get a response for that in the Q&A that we send out. But that's a good question. Because yeah, sometimes engineers do choose to do some kind of like little key down here to improve that connection. So let me look into that and see exactly what the program's doing.
All right. Question from Ronald, just clarifying how the outputs show area of steel on the selected rebar and spacing capacity comparison. Can we go back to where you were looking at the output
Yeah,
results and how it shows area of steel
yeah,
results?
we can check that. Rebar detail. Now that we need it, I've lost it. There we go. I'm not sure if there's a specific question in there or if they just wanted to kind of take a look at that.
Yeah, I just wanted to briefly revisit that for Ronald's question. So,
Yeah, everything will be in inch squared per foot because we're looking at a
yeah,
12
a
inch
unit strip
design
analysis.
strip. Yeah. So that's all going to be looking at how much rebar is required in that 1 foot strip that we are designing.
Yeah, and that required area obviously is going to be based off of both your minimums that were input and based on your flexural analysis for the stem.
Yeah. So for the most recent, I think IBC 2024 ACI 31819, it'll be based on your 0.0018 percentage and then your reinforcement required for your applied moment.
Sort of a related question from Bill. Why does the wall cross section show two sets of reinforcing steel for horizontal bars? Is this controllable in the module? I don't think you have a toggle to explicitly indicate that you want your sketch to show only one layer of horizontal temperature and shrinkage bars. I think that's just like Chelsea was saying earlier, that's just a graphical representation of the horizontal bars in the wall. I don't think you have a manual input to control those graphics. Chelsea, go ahead if you have thoughts on that.
Yeah, you're right, Seth. There is no manual input to control that graphic. It's more of it's not totally representing exactly what might be in your wall since we don't explicitly um, show that in the graphic. But when you look at your horizontal reinforcing outputs, you will always see the option for 1 layer or 2 layers for that temperature and shrinkage steel. So you have that information that you can use to decide what is appropriate.
Perfect.
I know this module is very popular for a lot of our users, and a lot of good questions likely came out of this. So I do just want to remind everybody that if there's anything pending that we can't get to, we will be following up with a written Q&A response. And if there's anything additional that we need to dive into, you can always reach out to support and we'll work with you to make sure that you get your questions answered.
All right, going down our list here. How is an area surcharge pressure beyond the end of the footing handled with respect to overturning and sliding? I don't see this pressure in the example diagram. So when a heel surcharge is defined, it's considered to be uniformly applied to the top surface of soil over the heel. Um, you can always reach out to the support team if you want to dive deeper on that, or if you're seeing something in your calculation that you don't expect.
Yeah. If this provides any kind of clarity, the heel surcharge is always going to be vertical, whether or not you have a sloped or a level back slope. And then when Enercalc is converting this load into a lateral load, it's going to divide your surcharge by your soil density and then multiply it by the active pressure coefficient to add some additional loading over here. So you're going to see that when you apply a surcharge up here, you'll see this active pressure value change down here to reflect that additional surcharge pressure. But as Seth said, if you have a specific question, we're happy to review your calculation.
All right. Well, Chelsea, we're getting down to almost 10 minutes after the hour, so we're probably going to wrap this up pretty soon here. But like Chelsea said, we are going to reach out to those whose questions we weren't able to answer. So stay tuned for those. And of course, for the recording from today, Chelsea, do you want to close us out with a teaser for next month? A little information about August 2025 office hours.
Yeah. Yeah, I just want to thank everybody real quick for being here. We really appreciate your time. We know that you're busy and we appreciate you being here with us. I'm excited to see a lot of good questions coming in. So we'll make sure to follow up with you guys to make sure that you get those answered. And then next month's office hours is going to be on August 13th. The topic for that session is still being decided. So keep an eye out for the follow up email that we'll send sometime next week. And that's where we'll be announcing the topic. So you can start getting excited for it. And I just hope everybody has a great week and is enjoying hopefully some nice weather wherever they are.
All right. Well, once again, thank you everybody for being here. We always look forward to these every month. We appreciate everyone's time and jumping in with great Q&A. If you did not see an answer to your question today, stay tuned for the additional answers that we'll be trying to put out for those. And then if you had a question that does involve deeper troubleshooting, or you need the support team to look at a specific problem or project file you have, absolutely follow up with the support team at support@intercalc.com. Thank you all very much. We'll look forward to seeing you guys next month.